Hello students, welcome to Rank High online classes. Our today's topic is quantum numbers. This topic involves quantum theory and is taught in 12th standard or higher. In the recent years, a lot of conceptual questions have appeared in JEE main and advanced papers also. So guys, be with me, try to understand the concept, and of course, if you have any queries, do not hesitate to comment below or WhatsApp me. I will revert as soon as possible. So let us start. Electrons can behave as particles or as waves. Schrödinger formulated a non-relativistic partial differential equation that took account of wave-particle duality and described the location and properties of electrons in atoms. The acceptable solution of Schrödinger wave equation gives wave function psi, a mathematical function of the position coordinates x, y and z which describes the behavior of an electron. The probability of finding an electron at a point in space is psi square, the probability density. The Schrödinger wave equation is as follows: nabla square psi plus 8 pi square m divided by h square into e minus v multiplied by psi equal to 0, where nabla square stands for the Laplacian operator, h is Planck's constant whose value is 6.626 into 10 to the power minus 34 joule second, m is mass of an electron, E and V are total energy and potential energy of the system respectively. Schrödinger wave equation can be solved exactly for a number of simple systems, as for example hydrogen atom, helium plus ion or lithium 2 plus ion, and can be solved numerically for many more complex systems, as for example multi-electron atoms and molecules. Each of the wave functions obtained by solving the Schrödinger wave equation for a hydrogen atom is uniquely labeled as a set of three integers n, l and ml called quantum numbers. Each quantum number specifies a physical property of the electron. In addition to the three quantum numbers required to specify the spatial distribution of an electron in a hydrogenic atom, two more quantum numbers s and ms were introduced to define the state of an electron after incorporating relativity theory into the Schrödinger equation by Dirac in 1928. These additional quantum numbers relate to the intrinsic or inbuilt angular momentum of an electron, its spin. Because the spin state of an electron must be specified if the state of the atom is to be described fully, it is common to say that the state of an electron in a hydrogen atom is characterized by four quantum numbers: principal quantum number, that is n, azimuthal quantum number L, magnetic quantum number ml, and spin magnetic quantum number, that is ms. We will discuss the principal quantum number first. Proposed by Niels Bohr, principal quantum number n tells us about the size of the electron wave and the successive major energy levels of the electrons in an atom. It has integral values 1, 2, 3, etc. and is denoted by k for n equal to 1, L for n equal to 2, m for n equal to 3, so on, which are called the cells. This quantum number helps to explain the main lines of the spectrum on the basis of electronic jumps between the cells. It gives the average distance of the electron from the nucleus, that is the size of the electron wave. Larger the value of n, larger is the distance from the nucleus. It also determines the successive energy levels of the electrons given by the expression E equals negative z square m e to the power 4 divided by 8 epsilon 0 square h square n square, where z equal to 1 for hydrogen and hydrogen-like species. We can see as n increases, the magnitude of E decreases, but due to the negative sign, the actual energy of the electron increases. Increasing values of n thus indicate the successive higher values of the energy of the electron. Order of energies of cells: K having lower energy level than L, which is having lower energy than M, and so on. The zero energy for n equal to infinite corresponds to the electron and nucleus being widely separated and stationary. In a hydrogenic atom, all orbitals with the same value of n belongs to the same cell, have the same energy and are said to be degenerate, whatever their values of azimuthal quantum number L and magnetic quantum number ml. However, for multi-electron species, the orbital energy depends on both principal quantum number and azimuthal quantum number. It is also used to calculate the maximum number of electrons in a cell, that is energy levels as designated with K, L, M, N, etc., which is given by 2 into n square since one orbital can occupy maximum 2 electrons. This rule is also known as Bohr-Bury's rule. Now comes the azimuthal quantum number. Proposed by Sommerfeld, azimuthal quantum number describes the shape of the electron cloud and the number of subcells within a cell. It can have values from 0 to n-1. That is, for a S subcell which is spherical in shape, L equal to 0. For a P subcell which is dumbbell in shape, L equal to 1. For a D subcell which is clover leaf in shape, except the dz square which is dumbbell donut shape, L equal to 2. And for L equal to 3, there will be a F subcell which is having complex shape. The azimuthal quantum number is also known as the angular momentum quantum number or subsidiary quantum number, which explains the fine structure of the hydrogen spectrum. Now you may want to know a little history about azimuthal quantum number. The movement of an electron from one orbit to another should give a single sharp line in the spectrum, but hydrogen spectrum, if observed with a high resolution spectrometer, shows a fine structure, that is composed of multiple lines. This behavior was explained in terms of elliptical orbits by Sommerfeld. Circular orbit is a special case of elliptical orbit when the length of major axis becomes equal to the length of minor axis, then the shape of orbit will be circular. If electrons revolve in elliptical orbit, then its angular momentum shows two quantum numbers. Number 1 a radial quantum number nr and 2 an azimuthal quantum number k, which are related to the principal quantum number n as n equals nr plus k, and major axis divided by minor axis is equal to n by k. For n equal to 1, there is a circular orbit, that is n by k value equal to 1 by 1. But for n equal to 2, there are two orbits. For n by k equal to 2 by 2, there is a circular orbit, and for n by k equal to 2 by 1, there is an elliptical orbit. Similarly, n equal to 3 possesses one circular orbit for n by k equal to 3 by 3 plus n minus 1 or 2 elliptical orbits, that is n by k equal to 3 by 2 and 3 by 1. The azimuthal quantum number k has now been replaced with L, where L equal to k minus 1, and L may have values 0, 1, 2 and so on to n minus 1. However, the accurate representation of subcells in an orbit is obtained with quantum mechanics. This quantum number is used to represent a subcell. Each cell has the subcells equal to the cell number. All orbitals of a given cell with the same value of L belong to the same subcell. A subcell can be thought of as sub-energy level inside a particular energy level or cell. As for example, for K cell n equal to 1 and L equal to 0, which represents one S subcell. For L cell n equal to 2 and L equal to 0 and 1, which represent 2s and 2p subcells. For M cell n equal to 3, L equal to 0, 1 and 2, which represent 3s, 3p and 3d subcells. For N cell n equal to 4, that is L equal to 0, 1, 2, 3, which represent 4s, 4p 4d and 4f subcells. The letters S, P, D and F come from the spectroscopic terms sharp, principal, diffuse and fundamental, which are used to describe the lines of hydrogen spectra. The order of energy levels of various subcells present in a same cell is S less than P, less than D, less than F, less than G, less than H and so on. The magnitude of orbital angular momentum of an electron, that is mod of capital L, can be determined with the help of azimuthal quantum number, that is small l. The energy of a rotating particle, that is an electron, in an orbit is related to its angular momentum. The linear momentum p of a particle of mass m and velocity v is defined classically by p equal to mv. Let r be the vector from the origin, that is the nucleus, of a coordinate system to the particle. The particle's angular momentum capital L with respect to the coordinate origin is defined classically as a vector of length rp sin beta and direction perpendicular to both r and p, where beta is the angle between r and p. More concisely, capital L equals r cross p, where cross sign indicates the vector cross product. Now, to relate the classical angular momentum vector capital L with quantum mechanical operators, we get mod of capital L equal to square root of small l into small l plus 1 into reduced Planck's constant. In this expression, small l is the azimuthal quantum number with values from 0 to n minus 1, where h by 2 pi is the natural unit of angular momentum and is equal to 1.054 into 10 to the power minus 34 joules second. A subcell with azimuthal quantum number L consists of 2l plus 1 individual orbitals, and the number of electrons is determined by the expression 2 multiplied by 2l plus 1. Now we will discuss the magnetic quantum number. Proposed by Lindy, the magnetic quantum number determines the orientation of the orbital angular momentum vector of the electrons in a subcell with respect to an externally applied magnetic field. This allowed the orientations of the electron cloud within subcells are those for which the components of orbital angular momentum vector capital L along the direction of the magnetic field, that is conventionally on the z-axis, which is expressed as Lz as follows: Lz equal to ml into h by 2 pi, which is also equal to ml into reduced Planck's constant. Under the influence of external magnetic field, electrons of a subcell can orient themselves in a certain preferred regions of space around the nucleus called orbitals. The orbital angular momentum capital L has components in x, y and z axis. In the absence of an external electric or magnetic field, the choice of the z axis is entirely arbitrary. But when such a field is applied, a unique direction is defined that becomes the axis of quantization. The azimuthal quantum number specifies the magnitude of orbital angular momentum, whereas the magnetic quantum number specifies the z component. The possible orientations of the angular momentum vector capital L with respect to a particular direction are shown here for azimuthal quantum number 2. In the absence of an external magnetic field, the choice of the z-axis is entirely arbitrary. But when such a field is applied, a unique direction is defined that becomes the axis of quantization. Since the Lx and Ly components are unknown, L can be described only as being in the surface of a cone, as illustrated in the figure. For example, a d subcell of an atom L equal to 2 consists of 5 individual atomic orbitals that are distinguished by values of ml equal to +2, +1, 0, -1 and -2. For magnetic quantum number equal to 0, the cone becomes a circle in the xy plane. So, L can lie anywhere on the surface of a cone about the z-axis passing through the nucleus. The possible orientations of the angular momentum vector capital L with respect to a particular direction are shown here for azimuthal quantum number equal to 2. So we can write the z component of orbital angular momentum Lz equal to ml into h by 2 pi, where ml is magnetic quantum number may have 2l plus 1 values ranges from plus L to minus L including 0. Total possible values of ml, that is the number of orbitals in a given cell, is n square. This quantum number is required to explain the additional spectral lines that appear when the atomic spectra of zinc or cadmium were analyzed by placing the source between the poles of a powerful magnet. This was first observed by Zeeman and also known as Zeeman effect. Here I have summarized the principal quantum number, azimuthal quantum number and magnetic quantum numbers in tables, where n corresponds to cell, L corresponds to subcell, M corresponds to orbitals within same subcell. Orbitals of the same subcell have equal energies are called degenerate. As for example, Px, Py and Pz are degenerate orbitals. Number of degenerate orbitals for S subcell equals to 0. Out of the two sets of F orbitals with 7 orbitals in each, general set is mentioned in the table. Cubic set comprises of different sets of 7 F orbitals might be appropriate if the atom is in a cubic environment. In addition to the 3 quantum numbers required to specify the spatial distribution of an electron in a hydrogenic atom, 2 more quantum numbers S and Ms are needed to define the state of an electron. These additional quantum numbers relate to the intrinsic or inbuilt angular momentum of an electron arises from the motion about its own axis called spin. Now comes the spin quantum number. Working on the assumption by A. Compton, Uhlenbeck and Goudsmit in 1925 proposed the idea of spin angular momentum of electron. Finally, in his relativistic quantum mechanical equation for a single electron system, Dirac in 1928 predicted an existence of intrinsic or built-in angular momentum independent of any orbital angular momentum. This angular momentum arises due to the spin motion of the electron about its own axis and called spin angular momentum or capital S of magnitude mod of capital S, which is expressed in terms of spin quantum number small s. Similar to the orbital angular momentum capital L with a magnitude of mod of capital L, we can write mod of capital S is equal to square root of small s into s plus 1 into h by 2 pi, which is equal to root 3 by 2 into h by 2 pi, which is also equal to root 3 by 2 into reduced Planck's constant. Similar to orbital angular momentum capital L, spin angular momentum capital S is developed in the electron due to its spin motion. The magnitude of capital S is mod of capital X and is described as mod of capital X equal to square root of small s into small s plus 1 into reduced Planck's constant, where small s represents spin quantum number and has single unchangeable value small s equals 1 by 2. The z component of spin angular momentum, the Sz equals ms into reduced Planck's constant, where ms is spin magnetic quantum number may take only 2 into small s plus 1 or 2 values, that is plus up for clockwise spin or spin up or alpha electron and denoted with up arrow, and minus up represents anti-clockwise spin or spin down or beta electron and denoted with down arrow respectively. From the spectral data, it can be shown that spin quantum number small s can only have single positive value, that is small s equal to 1 by 2. The spin angular momentum vector capital S has 2 into small s plus 1 possible orientations. If we put the spin quantum number plus half in these expressions, we get 2 possible orientations of angular momentum vector capital S with respect to magnetic field conventionally projected on the z-axis. This space quantization of electron spin, that is the z component, is described by a spin magnetic quantum number ms, which should not be confused with spin quantum number small s. Z component of spin angular momentum vector capital S is given as capital Sz equal to ms into h by 2 pi. Similar to relationship between magnetic quantum number and azimuthal quantum number, value of ms goes from plus s to minus s in integral steps and may have values plus half and minus half with spin either in clockwise or anti-clockwise direction, and can be expressed with sign up arrow or alpha and down arrow or beta respectively, so that Sz equal to plus minus h by 4 pi. The spin magnetic moment mu s of an electron is related to its spin angular momentum capital S. Mu s equal to negative of charge of electron divided by mass of electron into capital S, that is equal to plus minus charge of electron into Planck's constant divided by 4 pi into mass of electron. This quantity is known as Bohr magneton. The spin quantum number is the characteristics of a type of subatomic particle, and all electrons, protons and neutrons have the same value for their spin quantum number, that is equal to 1 by 2. Photons are relativistic entities travelling at speed of light, which have spin quantum number equal to 1 and spin magnetic quantum number equal to plus minus 1. These two ms values correspond to left and right circularly polarized light. Maximum spin of an atom equal to 1 by 2 into number of unpaired electrons. Each orbital can accommodate 2 electrons with opposite spin, are called spin paired. Paired electrons cancel the magnetic moment and develop mutual magnetic attraction. Electrons having same spin are called spin parallel. Both spin paired and spin parallel are shown below. Now I will elaborate a few facts about the orbital angular momentum and spin angular momentum. Both the orbital angular momentum and spin angular momentums are angular momentums and can be vectorically added to give the total angular momentum j. That is, we can write j vector equal to vector L plus vector S. We can also write the modulus of total angular momentum j equal to square root of small j into small j plus 1 into h by 2 pi, where j is mechanical moment quantum number with values L minus S where L is greater than S and S minus L where L is less than S. Spin multiplicity describes the most stable electronic configuration of an atom and is given by spin multiplicity capital M equal to 2 into sigma of spin quantum number plus 1, where sigma of spin quantum number is the resultant of all individual spin quantum numbers. More spin multiplicity means more stable electronic configuration. Here we have to remember one vital thing. Sometimes the spin quantum number is used in place of spin magnetic quantum number and written as small s equal to plus minus half, which is absolutely wrong. The spin quantum number is never negative and always equal to 1 by 2. That denotes the magnitude of spin angular momentum. For the z component only, we can write the spin magnetic quantum number equal to plus minus half. The spin quantum number helps to explain the magnetic properties of substances. If atoms containing only spin paired electrons are placed in a magnetic field, they are weakly repelled by the field. This phenomena is known as diamagnetism. Conversely, atoms containing one or more unpaired electrons are attracted by the magnetic field. This behavior of unpaired electrons is named paramagnetism. The attraction of each unpaired electron is many times stronger than the repulsion of all the spin paired electrons in that atom. To avoid confusion, I have tabularized the orbital angular momentum and spin angular momentum here. The angular momentum vector for orbital angular momentum is capital L and that for spin angular momentum is capital S. The magnitude of capital L equal to square root of small l into small l plus 1 into h by 2 pi, and that for spin angular momentum is square root of small s into small s plus 1 into h by 2 pi. The z component of orbital angular momentum is Lz equal to ml into h by 2 pi, and that for spin angular momentum is equal to Sz equal to ms into h by 2 pi. Orbital angular momentum quantum number or azimuthal quantum number is 0, 1, 2, 3 and so on up to n minus 1, and the spin angular momentum quantum number is small s equal to 1 by 2. The value for z component of L, that is ml, varies from minus L to plus L including 0, and the values of spin magnetic quantum number is plus minus 1 by 2. So that's all about quantum numbers. I hope the topic is very clear to you now. In the next lecture, I will come up with a few examples and recent year's JEE main and advanced questions from this topic and solve them. By this time, if you have any queries about this topic, comment below or WhatsApp me at 98319 12465. Till then, thank you and goodbye.